Okay, let's see if I can do this quickly. 4 forces act on the ladder, right? What are they? Weight, right? Normal force from the floor. I don't know what the vector length should be there, but whatever. Friction from the floor that keeps it from slipping out, yeah? And normal force from the wall. And you get to pick where you choose to be the pivot. Okay, so you could choose here, or you could choose here, or you could choose here, right? So conventional wisdom says choose the spot that's the most complicated, because since torques are R cross F, if you put the pivot where the most forces are acting, when a force acts directly on the pivot, it doesn't produce a torque, right? So if I have a door and it's got a hinge here, if I push here, yeah, at some R from the hinge with my force, then I have a nice torque. But if I push there, right at the hinge, I don't turn the door at all, because R cross F is torque, and if there's no R, right, because the R is measured from the pivot to the point of application of force. So in the blue case, there is no torque, but in the green case, right, there's the force, there's R from the pivot to the point of application of force. Okay, so that's what you need to keep in mind there. And okay. Okay, so on here, 22, they want the acceleration of the blocks. I feel like you could get this any number of ways, but I would consider sum of the torques equals I alpha. 23, the torque, 23A, the torque comes from gravity. There's a counterclockwise torque, RF, and that would be R mg, and that would be, yeah, so let's see. Light rod pivoted, so the heavy mass is the distance R. So the pivot is here. No, it tells me the pivot is here. So that means we have an R cross mg and an L cross mg. So I would say that the net torque is the difference between those. And in order to find the angular acceleration initially, you need to find the rotational inertia I for the system, and just remember your base equation is mr squared. Then I would use torque equals I alpha to solve for alpha. 24, the thing to remember is if the wheel's center doesn't move, then the tension is balancing with the mg. And the tension does, of course, exert a torque, R cross F there, so you ought to be able to operate from there. Don't forget that alpha is A over R. If we look at 26, 26, you're going to want to use Newton's second law for translation, sum of F equals ma. For rotation, sum of the torques equals I alpha. I personally like to solve for tension over here in sum of F equals ma. and then put that tension into sum of the torques equals I alpha, or R cross F, where F is the tension. So I'm going to solve for the tension over here in the linear Newton's second law, put it in for tension here, and if they want acceleration, if they use that word, they mean linear acceleration. So, so what that means is, let's see, Newton's, could you just, okay, so Newton's second law would be sum of F equals ma, and I could, sum on that guy, and this would be sum of the torques equals I alpha, add alpha, or R cross F, right, where F is F tension, and over here tension is going to be one of those forces. If I sum on this, then tension up minus mg down, probably. Is this what, 20? Okay. So once you solve, you're going to find tension. You're going to isolate tension here. You're going to plug it in here, equals I alpha. And the thing to remember is that alpha equals A over R. And so you want to put that in there. And what happens is usually a bunch of R's cancel out. And this A is linear acceleration, right? So just regular acceleration, not angular. Okay, so there's that. Let's stop this. Let's go back to, hold on guys, I lost it. Lost my marbles. That looks like part 2. Oh, part 1. Okay. So we're trying to look at, almost there, that was 26, right? So 20, looks like 27 is pretty heavy duty. What's it, 27, 27, 28, 29, 30. Okay, so let's go to 27. I know you don't have odds, but I just want to give you the idea, right? Since the system is balanced, there's no acceleration. The tension is balancing with the weight on either side. So figure that out any way you want to. Sum of F equals ma for B, right? Sum of F equals ma on the left one. And the rotational inertia of the pulley, I think I would do the sum of the torques equals I alpha and solve for I. Moving forward, this is a different kind of problem where you've got these two wheels. The angular speed of the larger wheel. The thing to remember on this type of problem, and it's important because you'll see it again, is that the linear speed of the chain is the same for both wheels. Okay? The linear speed is the same for the small and the large wheels. So I think you can say V equals omega R, right? So if V is the linear speed, then omega R equals omega for the, I guess, hold on, I'm going to back this up for a second. Okay, so if omega for the left wheel times, hold on a second, RR, the larger wheel is fixed, motor, pulley, blah, blah, blah. Linear speed is the same. So I guess I would say omega R equals omega 2R, and trying to remember, is the big one, I mean the big one must be twice the little one. Is that what it is? Do they tell us that? I'm looking. Pulley of radius R. Masses are removed, tied, connects the pulley to a larger wheel that has twice. Okay, so 2R is the big one, right? So I'll just say omega of the big one. And let's see what they want. Angular speed of the big one. So that's what you'd be solving for, right? What's the angular momentum of the big one? L equals I omega, of the big one. And what's the total rotational kinetic energy of the system? Would be the rotational kinetic energy of each wheel. So it'd be K equals 1/2 I omega squared plus 1/2 I of the big one, right? Omega of the big one squared. Okay, good enough. That's not so bad. All right, moving on. Let's see, 28. So first analyze the torques on the pulley. Then analyze the torques on the pulley. Remember that alpha equals A over R. Note that the tensions on the left and the right are not the same. This is critical, okay? An outward machine, blah, blah, blah. Mass this. So we've got mass B. And two masses, M and M, are connected by a light string. Right? They're different. Okay, so we've got a tension on the left and a tension on the right, and they are not the same. Now you need to consider for the acceleration of the masses, I would say R cross F equals I alpha. F is going to be left, so R cross F equals I alpha. R cross F is tension, but it's the net tension. So tension left minus tension right equals tension net. And that's going to equal whatever the rotational inertia is times alpha or times A over R. At this point, you need to go to Newton's second law translationally. And I think I'm going to send you a picture to help with this one. I think I'll just send it in Remind. So I think it'll just be more effective. So moving on, let's look at 29 real quick. 29, two small spheres, light rod. That means I don't consider the mass of the rod. A force is applied at a distance D equals something L over B from one of the spheres. D is, I wish I could see numbers. One of the spheres that is shown, D is some number times L over some other number. Okay. Remember, the linear acceleration is A, so sum of F equals ma. The total mass of the assembly is 2m. The angular acceleration, remember that both masses are half L from the center of the rod. So the rotational inertia should be 2m, right? mr squared, but m is 2m and r is half L. So 2m, 1/2 L squared, or 1/2 ml squared. The force is applied at R, which is 1/2 L minus D. So the force is applied at R, which is 1/2 L, right, minus D. And then I would use I alpha equals R cross F, solving for alpha. Let's see. And on 30, we need to do 30 together. So, yeah, yes. All right.